In this video, I'll talk about the design parameters for a water supply system. There are a few essential variables we need to decide before going in details about the design. First, we need to know how long the structure is expected to be in service, and that will provide us the design period. Is it 20 years or 30 years or 10 years? The duration is the design period. Okay, once we fix that duration, that is the design period. Next is the design population, which gives the number of people to be served by the proposed infrastructures. Is it 20,000 population or 50,000 or 100,000 or 10,000? So what is the population to be served? Design flow provides the maximum flow the structure is going to handle. Design area shows the extent of the area to be served, and design hydrology evaluates the source by analyzing the catchment rainfall runoff processes. Now, this design hydrology provides if the source has enough capacity to supply the design flow or not. Okay, so first we know the demand, and then we look at the available sources, and to find out if the source has enough capacity, we need to do different hydrological analysis. Once the area to be served and capacity of source is confirmed, we calculate what is the design period, what is the design population, and finally the design flows. All this analysis is to get the right design demand or design flows. Once we know the design flow, that information is used in the design of our hydraulic systems. So what should be the size of the storage tank? What should be the size of water treatment system? That all depends on the calculated design flow. So that's quite important in the success of the structure. So the right design flow is the most critical part. Now let's talk about different parameters. The first one is the design period. Design period means for how long the structure is expected to provide the service to the design population. As you know, longer the period, larger the project cost, and the project will be larger and the cost will also be larger. There are several other factors to be considered when deciding design period, such as useful life of component and structures. If a majority of the components of the structure's life is, let's say, only 20 years, then there is no point of designing the whole structure for 30 years. So the useful life of component structures and the equipments will decide what should be the right design period. Ease or difficulty to enlarge the complicated works is another factor. If you are constructing in an urban area with high traffic, it is important to have longer design period so that there will be less disruption to the public life. What is the future population growth? That is another factor, right? And can we forecast the future population growth correctly? That's another factor. So if the population growth is relatively constant and rightly predictable, then we can have a relatively larger design period. However, if there is a high population growth, then there will be higher uncertainty about the future demand, and there may be much bigger infrastructure requirement very soon, or the proposed infrastructure may not be used to its capacity. So in this kind of uncertain situation, it is better to use the shorter design period. Next one is the interest rate. For any capital infrastructure, you'll need to take a loan and you need to pay the interest rate. So if the interest rate is low, then it may be worth to consider larger projects or larger design period. If you have a massive structure to service for a long period, but if the initial usage is low, then it may affect the performance of the structure, right? And that's why the performance of the works needs to be considered, especially the early uh, during the early years. But these are the only few points to consider when deciding the design period. There are other factors. Obviously, there are other factors as well. Now, these are the typical design periods for large dams and conduits. Because they are hard and costly to enlarge, you typically use 25 to 50 years as a design period. Well, distribution system, filter plants, which are easy to extend, then you use 10 to 25 years of the design period. Now let's look at the population. We need to know what is the future population. Population increase by birth and decrease by death and changes with migration. All projects are designed not for today's population but for forecasted future population within the design period. So what is going to the population of the area at the end of design period is very important. To forecast the population, there are several mathematical models. Some are very simple. We just use the trend of the past to forecast the future. The last 20 years of data, you draw the trend line and then you forecast the future. Whereas the population growth is not that simple because there are other factors that affect, for example, education and employment opportunities in the area, lifestyle choices available, climate, pollution, and so on. So many other factors needs to be considered. So the figure here shows the historical population statistics in Australian capital cities. We can see some cities have grown significantly larger than others, right? So even within Australia, there are some cities which are growing much faster than others. So the figure, so the point here is that if you look at this trend, let's say this Sydney example, the top one, if you are designing the structure, for example, if you are designing at this point on time, and then if you just look at the trend, your forecast will be the population will be somewhere here in 1960 if you forecast in 1946, but actually the population is much larger. And then if you um, design your population based on the previous trend only, then your infrastructure will not be able to service the community at that time. So the point is, it's not only the past trends of the population, but also you need to look at the other factors. Now, if you are designing as a design engineer, if you are designing any water infrastructure, you will get the population projection from the local councils. They would have a short and long-term population forecast, and you can use that information in your design. Now let's look at the design flows. After we decide the design population, we need to know what is the design demand. Okay, once we know the design demand, that means what is the water demand of the population and what is the number of population. If we multiply that and then we get the design flow. So let's say design population in 100 people and design flow is 1 liter per day, then we can figure out that design flow is 100 times 1, which is 100 liter per day. But how much water is going to be consumed by the people, and that's another highly variable factor. Now, this water demand can be classified as domestic, residential, commercial, industrial, public, and some unaccounted water consumption that include losses. And as I just mentioned, water consumption is not constant. It depends on the climate, standard of living, type of residence, type of industries, water pricing in the area, quality of water in the area, and so many other factors. However, the problem is that we need to come up with some kind of value, some kind of information about the future water consumption. After, if our design period is 30 years and we are designing a water infrastructure today, then we need to know how much water people are going to use in 2050, right? Which is very complex. But we need that information. Otherwise, we can't predict what is going to be the design flow. We cannot come up with some figures. So somehow we need to come up with that design demand at the for the future population. Now let's see the domestic water consumption. This is just a snapshot. Okay, here we can see water consumption breakdown. 41% of water goes for flushing, 30% for washing and bathing, and so on. But this is just an example. Water consumption at one particular location at one particular time. It depends on location. You may use 30% of water for washing and bathing in one particular location and one particular day, but you may use it differently in different location, or in the same place you may use different values. Let's say you use 37% of washing and bathing today, but tomorrow you may use only 20%, and the day after you may use 50%. So even though water consumption is highly variable, we need to come up with some kind of value. And this kind of breakdown helps to find out what is the current trend and what is the likely future value. For example, if there is a trend of invention of toilets that use less water, than probably in future we may end up with using only 10% of water for flushing instead of using 41%. And that will help us to decide what should be the design demand for the future. Probably for drinking, there may not be changes, right? Or kitchen use, probably there may not be that changes, but for toilet flushing and washing and for all these uses, the percentage of use could be different. And it's not only domestic water consumption, for different industries also, what is the trend and what is the likely water consumption in future. So all these factors needs to be considered when you come up with the future water consumption. So that's the different factors we discussed about the um, design demand. However, if you work as a design engineer, you shall use water demand provided by your clients, typically the councils. So the councils or the clients usually provide consultants what demands they want to use for design purpose. Okay, and the figure here shows a very typical example. So 380 for residential, commercial, 115 industrial, 85, and public 65. So they will provide this kind of information. And so in your area, how many residential uses will be there, how many commercial, how many industrial, and then from all those information you can come up with the design flow. But as I said, this is a very typical, and every council would have their own design demand, own water demand. So you need to use the information provided by those councils. There are a few water demand parameters. Even though we talk about demands, the water demand can be further classified, and the main um, classifications are maximum daily demand, average daily demand, and peak hourly daily demand. So these are three different types of demands we use in our design. So we know we use water for 365 days, but we do not use the same amount of water every day. So let's say we record the usage of water for 365 days, and in your local distribution system, they have that kind of record. So every day, every hour, they record what is the flow, and that from that information, you will see how much water consumption is happening in the city. So if you have a record of 365 days, then you will have one absolute minimum value, which is the minimum daily demand, one absolute maximum value out of 365, that is the maximum daily demand. Average of all those 365 days will be the average demand. And also in your distribution network, you have the record of hourly water consumption, and that will provide you the maximum of 24 hours, and that is called the peak hourly demand. Okay, so that's all from the past information. Now, how are we going to use that information in our design? Now, let's look at a typical layout of a water supply system. We have a intake here, and then we pump the water from intake to the water treatment plant, which is generally close to the intake, but above the maximum flood level. So we don't want water treatment plant to be affected by the flood. Okay, so we put the water treatment plant above the intake, but also above the maximum flood level. 100-year flood, 500-year floods, that depends on the council, but it has to be above that flood level. Now, from intake to water treatment plant, you use the low lift pump, and after you treat the water, then you supply this to the service reservoir through the high lift pump, and finally from service reservoir to the distribution system. Now, when we design these different components, what design demands should we use? In this area, we have this hourly fluctuation of demand. We supply water to the individual customers, and then that means this distribution system need to handle the hourly fluctuation of demand. So the distribution system should be designed for peak hourly demand because it needs to handle the peak hourly fluctuation in the demand. Now, the service reservoir is mainly to balance the fluctuation of the demand in the distribution system. Okay, so for 24 hours fluctuation, it has some storage capacity, and then water level, the amount of water in the service reservoir fluctuates as the demand in the distribution system. Okay, but because of the service reservoir, you don't need to have these other components with the same design capacity. You can design anything before the service reservoir to the maximum daily demand plus reserve. You don't need to design for peak hour demand because service reservoir will balance the demand, and then anything before the service reservoir, you don't need to design for the maximum hourly. You just need to design for maximum daily demand plus the reserve. So this is a typical design discharge for different structures. Intake structure and conduit 1 can be designed with maximum daily demand. From there on, maximum daily demand plus reserve, and conduit 5, and the distribution system has to be designed for maximum hourly demand. This is an actual water supply from a reservoir to a township in for 1 year. Okay, the figure shows the daily water outflow from the reservoir. In this community, they have only one reservoir, which means the value represented here, while values that are present here is the total daily consumption by all the properties connected to that network. So from this figure, we can see the maximum daily demand is 800 meter cube per day. Okay, so that's not one particular property, but the whole township. The maximum daily demand is 800. And the minimum daily demand is 300. So you can see the fluctuation, so less than 300 to 800, right? And if you sum them all these daily demands and then average them, then you will get the average daily demand. To calculate the hourly fluctuation, you need to have the record of hourly demand, and then from that you can see what is the peak hourly demand. Now, the last one we need to consider is the fire flow. Once you have the demand for industries and residential and all those demand, another factor you need to consider is the fire flow. So besides the other uses we discussed, water for potential fire suppression should be included in your design. So the design flows is the summation of domestic use plus fire demand plus industrial use plus any other uses that is not discussed here and that are only typical to the particular area, plus the losses. There will always be some losses, and that also be included in the design flow. And the magnitude of fire demand has to be decided by discussing with local council and local fire authorities.